Okay, class. This lesson is a follow-up to the investigation we did in class on rational exponents. We went through and looked at some patterns as we um, looked at different bases and different exponents, which were fractions. This is a summary of the things that we've seen, and just a formal uh, note here for you to fill in. You have this package already, and you're going to be filling in information in these boxes. So I'm going to go through some examples, and at the outset, we're going to eventually come back in class to this investigate to try to take this formula, which gives us how fast a land mammal can run based on the stride length and the hip height. And we can estimate these from dinosaur fossilized tracks. So we're going to come back to that. I'm going to try to answer this question: how many different ways can we express that formula? I'm going to challenge you to try to come up with at least 3 ways to express that formula based on the exponent laws that we've learned at the end of this lesson. And then we're going to compare the way the different formulas look and try to answer this question: which are easier to calculate if we were to evaluate to a final answer. All right, first thing we want to do is define the power a to the exponent 1 over n. And we're just going to begin by looking at what we already know, which is the power of a power law. And we're going to extend that just to see how we can actually stumble upon the definition of this power a to the exponent 1 over n. So we know that by power of a power, we're multiplying exponents. And 2 examples are shown here, or two different problems. One is the square of 6 to the 1/2, and the other one is the square of the opposite, or negative 6 to the 1/2. Now in one case, we're going to apply power of a power, and 1/2 times 2 is 1. In the other case, we separate out the negative from the power, and we just identify that negative is really negative 1. And if we want to put an exponent in there, we'll put 1. So now what we're actually doing on the right side here is we're evaluating the second power of a product. And that just means that we're going to have to multiply or everything in the brackets here by itself twice. And so the power of a power law takes over and says, well, okay, we'll evaluate the outside power, the green exponent. We'll multiply that by each of the exponents inside the brackets. So we can separately apply the power of a power law both to the negative 1 to the 1 and 6 to the 1/2. So negative 1, when we square that, we multiply 1 by 2. When we take 6 to the 1/2 and square that, we multiply that exponent out, and we end up with 6 to the 1 multiplied by negative 1 squared. And negative 1 squared, of course, is 1. So our final answer is 6. Now all this just to illustrate that we have 2 identical answers coming from 2 different powers. When the power was 6 to the 1/2, we get the same result when the power was negative 6 to the 1/2. So what that tells us is that in the next step, well, 2 possible values can be squared to give the same number. And that only happens when we're applying the root operation. So because the square root of 6, when we square that, we get back 6. We have to remember that both positive and negative roots, when squared, will give the same value. And to give another example to help you follow along here, we can take negative 3 and square it, and negative 3 times itself gives us 9, but we get the same result if we took 3. 3 times 3 is also 9. So by the definition of square root, which would tell us that the square root of 9 is both positive and negative 3, we can be certain that when we apply the exponent of 1/2 to a number, what we're really doing is we're applying the square root. And so we could have replaced what was in brackets there with positive root 6 or negative root 6. Both of them, when squared, would give back 6. Okay, so that tells us that the exponent of 1 over n, at least when n is 2, is the square root. So that's the first thing which we can arrive at, is that an exponent of 1/2 is defined to be the square root of the number. So in the margin here, we see that there's a distinction between the positive root and the negative root. So most of the time, it's just the positive root that we're interested in. If the value has to be positive length, then we would have to just use the positive value. But there is also a negative square root. Now, by extension, if we were to continue this, we could see that if we were to take something and cube it, well, cubing it would give back the original value, just as squaring did when we start with the cube root. And so if we began with the cube root of 6 in brackets and cubed it, we would get back 6. That might look something like this. 6 to the 1/3 when cubed would give 6 to the 1. Or alternatively, if we had 6 to the 1/4 and we were to raise that to exponent 4, that would also give back 6 by the power of the power law. So by the definition, we must be using roots whenever we are applying a rational exponent. So this can be summed up as follows. The definition of a to an exponent 1 over n is the nth root of a. And written in sort of math symbols here, I want you to write down this in your box. Okay. There's only some conditions on this that we have to be aware of. N is a natural number. Natural numbers are numbers that start at 1 and count up the whole values. So these are the natural number sets. Okay, so n can't be a negative value. So we're not going to be dealing with base raised to the 1 over -5. Okay, that's not defined for this exponent law. The other condition, okay, so n must be a natural number. The other condition is that the base itself has to be 0 or more if n is even. Now, that one is kind of a special case. I don't think we're going to need to go any further with that condition, because all the bases that we will use in our examples are going to be positive anyway. So for our purposes, let's just simplify that and say a is a positive value. Okay. Okay, so we have defined a power of a rational exponent, rational meaning ratio, okay, or a fraction. And what we've discovered here with these examples is that rational exponents mean roots. Okay. Another word for a root that you need to know is a radical. Okay. So roots equal radicals. So when you come across that term and it requires you to put it in radical form, it means put a root symbol. Okay. So the nth root, what we mean here is the type of root. So a square root is the second root, fifth root, n is 5. Okay, I'm going to slowly move through some examples here just to give you some confidence with how this works. So the first example in the textbook, I'm just going to go through how these are solved, is in part A 49 to the 1/2. So 49 to the 1/2 is just simply the second root of 49, or the square root. Okay, now we don't need a calculator for that. We know that 7 squared is 49, but we should also remember that there are two possible answers. Okay, and the reason being is that 7 squared is 49, and negative 7 squared is also 49. So when we raise 49 to the exponent 1/2, which is the square root, we get a positive and a negative value. So there's actually two solutions to that. Now that's the case for even roots. For odd roots, we'll see that there's only one solution possible. So to the 1/3 is equivalent to the third root of the base. Okay, those are equivalent. Now the third root here means some number that, when cubed, gives back negative 64. Okay, so we're looking for a number multiplied by itself 3 times over to give negative 64. I think we should be able to at least say that the number is going to be a negative value, because 3 factors, all negative, would give a negative product. If it were only 2, the answer would be positive. Okay, if the values themselves were positive, we could never get a negative value. So the value has to be a negative, and we're thinking, well, what multiplied by itself 3 times over? Well, we know that 16 times 4 is 64, and 4 times 4 is 16, so the answer would be negative 4. Okay, so negative 4 is the number that, when cubed, gives 64. And since opposite operations are involved here, the opposite of cubing would be cube root. Second two examples, or the last two rather, I can't look at right now. We need to develop another exponent law. So we'll just move back to some more examples to look at the exponent law for rational values where the exponent is not always 1 over. Okay, I'm going to go through one more example here before we look at the exponent law a to the m over n. We'll come back to that. But here, that's not yet defined. What we do know is that a to the 1 over n is the nth root of a. So we can actually apply that exponent law when we're solving for equations. Here, solve for x, assume x is a positive value. So if we get a negative root, we're only going to take the positive value. So how would we solve this? Well, we do know that we can apply opposite operations, and we can say what the opposite of the exponent 4 would be the fourth root. So we could approach it like that. We could apply the fourth root of both sides. And the fourth root of x to the fourth would be x. Okay, now the fourth root of something is a value which multiplies by itself 4 times over to give the number. So what would that be? Well, 2 times 2 times 2 times 2 is 16. Now I'll also point out that, okay, so 2 to the exponent 4 is 16. So therefore, the fourth root of 16 is 2. However, also, negative 2 to the exponent 4 is 16. So really, the complete picture, when we take the fourth root of something, it would be plus or minus 2. Now, since we were assuming x is positive, this is the only answer we want. Okay. Now, the other way we can show this, so this is applying the fourth root. Another way we can show this is to take both sides, okay, as written, and raise both sides to the exponent 1 over 4. And this sort of directly shows why the fourth root undoes or reverses the exponent of 4. Is that if we take both sides and raise them to the exponent 1/4, then which exponent law would apply here? Well, we have a power of a power. And so we could simplify that by saying this is x to the 4 times 1/4. This is what confirms for us that when we take the fourth root of something to the fourth, we get just x, because 4 times 1/4 is 1. Okay, so we have just produced an exponent of 1. So again, one of our goals when we're trying to isolated variable is to produce a term of 0 when we're adding or subtracting, to produce a factor of 1, or to produce an exponent of 0. Here we've produced an exponent of 1. And so 16 to the 1/4, which of course by our definition is the fourth root, and then of course the math would finish up the same way. Fourth root of 16, which would be positive 2 if we're only taking the positive value. Okay? Okay, at this point, if you were struggling a little bit with that first exponent law, I would suggest you go back and just skim through it. It's really important you understand why we were looking at roots to establish that the exponent of 1/2 was the square root. It wasn't a coincidence there. Once that was established, the other examples weren't shown, but they could have been. Okay, so at this point, you should know that roots are related to rational exponents. And so when we look at a rational exponent where the exponent is a fraction, but the fraction doesn't have a numerator of 1, we should expect that radicals or roots are still going to be involved, but there's something that has to be adjusted because the numerator is a number other than 1, potentially. So the definition of the power a to the m over n, we can interpret this two ways. Okay, I would just show off to the side that m over n could be written as m times 1 over n. Okay, and because of that, we can separate out the fraction into something which we already know how to handle, and then a factor of that. Okay, so that allows us to take the power a to the m over n, and we can write that a couple ways. The first way is by applying the exponent 1 over n directly to the base, and then applying m outside of the brackets. Okay, so understand that when we take the two parts of m over n, we can multiply them back together to get the fraction. So in both cases, they're equivalent, but in one case, we see that, we know how to deal with a power of base a and exponent 1 over n. It's the nth root of a. So what that would allow us to do is say, okay, we can at least simplify that into radical form. And now this would require us to take that result and then raise it to some other exponent m. Okay, so that would be written in words: take the nth root of a, then raise the result to the exponent m. Another way we could interpret this, here's an example. Okay, so the first interpretation is, let's say we have a base 8 and exponent of 2/3. We could take this and write it as 8 to the 1/3 all squared. Okay, 1/3 times 2 is 2/3. We know how to handle an exponent of 1/3. It's the third root. That's what's done here. We know how to square something afterwards. That's what's done here. Okay, the answer would then be cube root of 8, which is 2, squared is 4. The second way we can interpret this is if we apply the exponent m first, and then we take the root after. Okay, and in that case, it's still the same. We're really just saying we can take 1 over n and multiply it by m, or we can multiply 1 over n times m. In both cases, we're still going to get the same fraction. Okay, now by changing the order here, we can do either the root first or the exponent first, meaning that we can either take the nth root first, or we can evaluate the power of m first. In the second interpretation, it's taking the numerator, applying that as a power, and then taking the root afterwards. So this would have us raise a to the exponent m, then take the nth root. You're going to have to look at these two and really see that they're equivalent and then decide which one do you identify most with. Okay, again, in the example here, we could first raise 8 and square it, which gives us 64, and then we could take the cube root afterwards, and the cube root of 64, of course, is 4, which gives us the same result. Okay, so you really need to see that these are both valid approaches, and they just change the order of the root and the power. Okay, so in general, what we're seeing here is that when we define a to the m over n, can be defined in two different ways. The nth root of a to the m, or a to the exponent m and the nth root of that. And again, the conditions here just need to be mentioned. The numerator, okay, which is m, needs to be an integer. What that will allow us to do is potentially use a negative value. Okay, integers are negative natural numbers, basically. So we have anything that is a natural number is 1, 2, 3. And integers are the positive and negative natural numbers. Okay, and it also includes 0. So m can be an integer, and that's important because if we want to use reciprocals, and we've already seen reciprocals with exponent laws, then we have to have the ability to put in a negative here. We don't want the root to be a negative. That wouldn't be defined at this point. So we keep the denominator, okay, the n, the denominator is going to be a natural number. But the numerator can be an integer. And again, as before, our base, as we mentioned, is going to be, as I mentioned before, it's best to just say that a is going to be a positive value for our purposes here. Okay. Okay. Now this is a challenging exponent law, and this is a little bit more challenging than just the multiplying powers, dividing powers, and the power of a power. So you're going to need to do a lot of practice with this, and you might need to view this video a second time and discuss these questions with your partners in class, and make sure you do all the practice questions before you submit your feedback question. So let's go back here to this example 1. Now that we've seen rational exponents and all their possibilities, we could generally just say that it doesn't matter whether m is 1 or not. We can use either one of these forms. We can either take a, raise it to exponent m, and then take the nth root of that, or we can apply the root first. And it really doesn't matter whether m is 1 or not. Okay, I hope you see that if m is 1, it actually makes it a lot easier. It's just this is the root, and m won't change that. Raising something to the exponent 1 won't change that. So I would really recommend that of these two exponent laws, this would be the one that I would focus on almost exclusively, because even if the numerator is 1, you can still apply this this law, and in both cases rational exponents involve roots, which are radicals. So when we raise something to the exponent 4/5, then okay, we look at the bottom, the 5, the denominator, is the root, and the numerator 4 is the exponent. So let's look at this. We could say either this is 32 and the 5th root of that raised to the 4. Okay. Or it's 32 to the 4 and the 5th root of that. Now 32 to the 4 is a pretty large number, whereas 32 the 5th root gets smaller. So my preference is to evaluate the root first. It brings the size of the number down usually, and then apply the exponent afterwards. And in the case of the 5th root of 32, it's 2. And then apply the exponent of 4 afterwards, we get 2 to the 4 is 16. What you should also be doing as you're going through these examples is practicing this with your calculator. See what happens when you take 32 and then say raise it to the 4 over 5, or 32 y to the x 4 over 5. And I would strongly encourage you to use brackets around this, because if you don't, your calculator may likely just apply the first number, because exponents has priority over division, and it may divide by 5 afterwards. So put brackets around your rational exponents when you're using a calculator. Now, we're not supposed to need a calculator here, and I would agree, you don't need a calculator. You should know that 2 multiplied by itself 5 times over gives you 32. You should know that 2 multiplied by itself 4 times over gives 16. So these aren't intended to be questions that really stretch you that much. Okay, the next part here in part D would be a little harder because this is a decimal, but we can handle an exponent of 3/2. So let's look at this. First of all, we can take it as the square root of 0.04 raised to the exponent 3. Now, 2 times 2 is 4. And 0.2 times 0.2 is going to be ending in 4, but it's 100th the size, because each of the values are 1/10 of 2. So we basically are going to be taking 4 and multiplying it by 1/10 and 1/10 again, which would be 100th of 4. Okay, so 0.2 times 0.2 is 0.04. Okay, 0.02 times 0.02 would also end in 4, but again, in that case, it would have three zeros before the 4. Okay, it would be like taking 4 and multiplying it by 100th and 100th again. Okay, so you should need a calculator for that. So the answer there would be 0.2, and 0.2 cubed is, well, 0.2 times 0.2 times 0.2 is going to end in 8, and it's like taking 2 times 2 times 2 and then multiplying it by 1/10, 1/10, and 1/10, which would be 1,000, so 0.008. Okay, another way you can think of this maybe is 0.2 is 0.1 times 2. Okay, I know some of you are going to say, I'm just going to use my calculator, but you know what? You need to develop the mental math here. Okay, this shouldn't stretch you that much to be able to do this in your head. So let's use what we've already seen. If we use power over power here, we can take the exponent and we can apply it to both parts of the product. Okay, and 0.1 times 0.1 times 0.1 is 0.001. Okay, so that shouldn't be too difficult to figure out that that's 0.008. Okay, so that would be our answer there. Okay, one more example here, and then I'm going to sign off this video, and there will be a second video that goes through the solutions to some practice questions in the textbook. This one here, solve for x. So it's another equation, and we're going to use exponent laws here. So what this is saying is some number x raised to the exponent 3/2 is 27. Now we could write that as we've learned, okay, that's the second root of x all cubed equals 27. Or we could write it as x cubed and then the square root of that equals 27. Okay, neither of those on their own are particularly different, and they don't necessarily lead us to the solution right away. But what we see in both cases is that we can do opposite operations on our left side so that we can get closer to x. So if we were to use, let's say, this first version here, I might say, well, opposite operations, what's the opposite operation of raising something to the exponent 3? It would be taking the cube root. So I could take both sides and take the cube root. Now, how do we take the cube root? Well, let's try to think of it using rational exponents. If we raise both sides to the 1/3, that's taking the cube root, okay? And that's an operation which we can apply to both sides. And on the left side, 3 times 1/3 gives us 1. So basically the square root of x to the 1 equals 27 to the 1/3. The third root of 27 is 3. Okay. Now we're getting closer to isolating x. On the left side we have the square root of x. What's the opposite operation to the square root? It would be squaring it. And I'm just going to replace square root of x with x to the 1/2 because I just want to reinforce this rational exponents idea. And again, the squaring of both sides produces x because really the power of the power. It's not so much that square and square root are opposite operations that really convinces us. It's that we know that the power of a power law is multiplying the exponents, and we know that a number times its reciprocal is 1. And so a half multiplied by 2 is 1. So no one is going to dispute that we have actually isolated x. We have solved for x. We've produced an exponent of 1 on our variable. 3 squared is 9, so that would be our answer there. Now, I'm just going to circle something here and point out that this other version that I wrote, I would not pursue that. And I hope you can see why. Because the two operations that we used were the cube root and the square. We want to square once the number is small, and we want to cube root early when the number is large. So it's better to cube root 27 and square afterwards than to square first and cube root later, because the square of 27 produces 729. And you may not know that the cube root of 729 is 9, but I'm certain you should know that the cube root of 27 is 3. And I think squaring 3 is a really easy operation. So when you apply this variation of the rational exponent law, I would apply the radical first. I would apply the root first and the exponent afterwards. Enough said. Okay, I'm going to stop at this point. Going back to what were the assigned questions, the last thing I want you to be doing is submitting the feedback questions. You need to be really devoting yourself to the practice questions. So in a small group, you're working on some questions and then independently doing a few that are application style questions as well. The second video, I'm going to go through the answers to this practice set of questions as well, which are also on page 377. And I'm also going to go over example 3, which is solving a financial problem that relates to compound interest. So at this point, review your exponent laws, make sure you've completed your worksheet and filled in the those boxes there. And you can start practicing in class tomorrow, and we'll spend at least a couple days on this, working towards that feedback set of questions. Take care.